Thank you for the okay. Thank you for the introduction. So today I'm going to talk to you about classifying images by combining these two topics, self-supervised and continual learning. So I'll go first over a quick motivation about these topics. Then I will go over each of the topics, self-supervised and continual learning, and then how we can combine these two topics to get better performance. And then I will have a quick summary and some final thoughts. So let's start with the motivation. In supervised learning, when we want to train, let's say, a neural network using this method, what we have is a set of images with labels. So for example, here we have 3 images, each of them with their labels, with the chicken, cat, and dog. And then we train the algorithm by showing images and labels. And then once we have trained, we can do predictions over some data that the network hasn't seen during the training stage. Now, how this is done in neural networks is by using a loss function. And in the supervised case, what you do is you compare your predicted class distribution with your true class distribution. And this true class distribution is the one that contains the labels. So basically what you want to do here is to say how good my predictions are compared to the actual labels. Now, this way of training has been successful during the last decade. So on this image on the left, you can see the error in classification on this data set called ImageNet, which has over 1 million images, over 1,000 categories. And then you can see that over the course of the years, we have been able to decrease that performance until the point where now we are better than human on classifying this data set called ImageNet. But there is an issue. The real world is not a static data set, right? This ImageNet data set is a finite set of data. We have this million of images, and we have labels. We always have these categories for each image. But in the real world, how we experience that is actually a stream of events. If we experience the visual world, we are just getting images all the time to us. And we might not have labels all the time because of the nature of this streaming of data. Labels might not be available right away. So if we want to learn from the real world, which has these two characteristics, we need to deal with those two. So there is something called continual learning, which deals with this characteristic of a stream of events. What they do is they accumulate and refine knowledge over time, but they are mostly supervised. They still use labels. And on the other hand, we have something called self-supervised learning that is able to learn features from images without using labels, but it's not continual. That means that it doesn't deal with this stream of events in time. So if we want to learn from the real world, we basically need to put these two together in some form of way if we want to learn representations efficiently from the real world. And this is now being called continual self-supervision. So with that motivation, now let's go into what is self-supervised learning. To understand that first, I need to show you this. When we train a neural network, this is like that architecture. We have 2 sections. We have one section that does feature learning. So this section, what it does is it's gonna learn to detect meaningful features from the image across all these layers. And then we have this other section called classification, where this second set of the network is going to look at these features and then it's going to come up with some prediction. So for example, if this image is a car, it should give me the label that is a car. The issue with this is that supervision is a bottleneck for feature learning. So that means that if we want to do this feature learning, if we want to learn features, we need the labels, right? But labels are expensive to obtain. So for example, on that ImageNet data set that I showed at the beginning, there were humans or a bunch of humans that they went through all these images and manually started writing what labels should have each of these images. So that's time consuming. And also you might need expert knowledge for this. For example, if you want to label some rare species of plants, you need someone that knows about that to label those. So you need to wait for all those labels to be created to do this feature learning. But the question here is, can we skip this? Like, can we not use labels? Can we just do the feature learning without depending on them? And that's what self-supervised learning does. It comes inspired from the success that they had in natural language processing. There are these big language models and they are trained in a self-supervised manner. But what that means is that now it will be able to do feature learning without using these category labels. And they do that by just putting a proxy task. So this proxy task is going to generate some pseudo labels that is going to help me to learn some features from the images. After training with that proxy task, how do we know if these features are good or not? So we need to evaluate them. And the way we do that is after we have trained those, we freeze this first set of the network, the one that is in charge of feature learning. So that means that we are not going to change those weights again. But now we plug in these classifications part of the network, and then we can grab some data set that has labels and then do the evaluation and see how good these features are. That's called linear evaluation. This method has drawn massive attention during recent years because they generalize better than supervised in some cases. And now it rivals supervised learning on this linear evaluation task that I showed before. So on the image on the left, you can see that over the years, the number of papers and citations has increased exponentially on this topic. And you can see this set of methods here, they are reaching now the performance of supervised learning, where this is showing you the top one accuracy on linear evaluation on image. So how this actually happens? Early on, methods that did self-supervised learning on images, they had this kind of proxy tasks. So since I don't have labels, I need to come up with something from my data. So one way is to do the colorization task where you try to predict the chromatic or the color of the image based on the luminance channel, which is just the black and white version of the image. You can have another task like rotation prediction, where you take an image, you rotate it some angles, and then you try to predict with the network what was that rotation. This is easy to do because the rotation angle is the one that you are imposing, so you will have that label right away. And then there is another one called exemplar, where you have an image and then you create a lot of different images with different perturbations. That's called data augmentation. And then you create a set that now this is going to be your class for that specific image. So here it means that the number of classes that you're going to have is the number of images that you have in your data set. So you don't need category labels, you just need how many images I have in my data set as labels. The issue with these methods, as you can see on the right side on this table, is that if you do the linear evaluation on ImageNet, they perform really bad compared to the supervised setting where you use labels. Even in this work, they try to improve the performance a bit, but it's still way, way lower compared to the 74 performance that you get on supervision. But current SSL methods or self-supervised methods, they do something more complicated than those proxy tasks. They are based on something called contrastive learning or some comparison between images. What they do here is if I have a set of images, let's say these two images, I'm gonna create two augmentations or two different views of this image by doing some perturbation. I will pass those through my network, which usually is a convolutional neural network, and then I will get some representation of those images in the feature space. And then what I want to do is I want to pull these two together because I know that these two came from the same image, but then the representations that came from different image, I want to push those far away. So what this is going to do is it's going to create image representations that are robust to these perturbations. And this is the method that now rivals supervised learning. So in this case, labels are not involved in it. We are just trying to push together these augmentations from the same image and push apart the ones from different images. One method that just does that is called SimClear. On this method, as I said before, you do the augmentations to your image, then you pass them through some functions, and these functions are just the networks itself. Like this could be a convolutional network, and this could be another network. And then at the very end, what you want is to maximize the agreement between these two representations. They use a loss where they enforce the similarity between the two augmented images that we know came from the same image, they want this to be higher compared to all the other pair of images that you can do when you do it with other images in that batch. And by doing this, they got a bit of a boost compared to all previous methods at that time. And all those previous methods, they were doing more complicated stuff. But it seemed clear with just doing this maximized agreement, they were able to get way better performance. But then this other method came in called swap, which, as you can see here now, this is the one that is really close to supervised when you use a network that has 25 million of parameters. But also, if you use bigger networks, you can also match almost the supervised performance. So on this method, you don't compare the images itself anymore. What you do is you pass your images, again, you do your two augmentations, then you pass them through the network. And then what you want to do is you want to compare the image with the cluster assignment on the other side of, or on the other branch. So what I mean by this is that they call it swap prediction. So having this representation C1 that came from one of the augmented images, I should be able to predict the cluster that the other augmentation was assigned to on this cluster space. And they do that by just trying to push the similarity between these two vectors together, C1 and the coast Q2 from the other branch, and vice versa for the other way. And this has shown to work really good, and that method has a performance that it hasn't been surpassed that easily. But now there is this other method called Dino. Now, on this method, what I can say is that if you see here on the linear evaluation again, it performs the same as swap, which is the previous method that I showed. But if you change the architecture, if you change, instead of using ResNet 50, you use something like a visual transformer, you get an improvement in performance on this method called Dino, but you don't get that for swap. So that means that this method is more general for different architectures. And the way it works is just by, again, you still do your augmentations. So you have these two augmented images, you pass them through the network, but now instead of updating your network on the two branches, you are only going to update one branch. And then the other branch is going to be exponential mean average. That means that this teacher network is just going to be a slow update from the weights that come from the student network. You pass those two through some blocks, then you get a softmax output on each block, and then how you compare those two, you just use a loss that is really similar to the cross entropy loss that we use in supervised learning, but now we don't have labels, we just compare these two. And this has shown to be more general to different architectures, as I said before. And there are many others. I won't go over all of them, but what I can say here is that on this linear evaluation setting on ImageNet, all of these methods, they still perform either lower or similar than swap if you're using ResNet 50. But all of them come with different flavors, different losses, and they have their advantages and disadvantages. But the main takeaway from these methods is that on all the previous performance that I have been showing you, it's always doing the pre-training stage on the dataset ImageNet, and then we do the linear evaluation on the ImageNet again. But what about if we want to evaluate on another dataset? We want to know how these features generalize better to different datasets. So that's what this table shows. What it's showing you is all these self-supervised methods and the supervised one that uses labels has been pre-trained with ImageNet. And then now we are going to test the classification performance on other datasets like places, VOC, or different ones. And we could also test in a different task. Instead of doing image classification, we could test those features on object detection. And as you can see, all the underscore numbers, those are the numbers that are surpassing supervised features. So that means that these self-supervised features generalize better than supervised when you test them on a different data set. So that's really good because that's gonna help a lot once I show you how we can combine this with continual learning. However, these self-supervised methods, they are using still this fixed finite data, right? It's the ImageNet data. We don't use labels, but the data is still fixed. But we still want to deal with these characteristics of the real world. So now we are going to jump into continual learning, which deals with the stream of events part. So in continual learning, what you want to do is you want to train your system and accumulate knowledge and refine knowledge over time. Something kind of similar that humans do, right? Like we learn some task and then we learn a second task during our lifetime. And usually we don't forget previous tasks. Now, how can you do that? Or how can you simulate that with some data set, for example, like ImageNet? You can simulate this stream of events by just setting an ordering of the classes that you're going to feed to your network. So, but there is a problem when you do this. If you have the common neural networks that we have right now, and you train them in this incremental setting, something called catastrophic forgetting happens. That means that it's going to forget, for example, if you learn the task 1 at some time, and then you learn to do task 2 and then task 3 in time, it's likely that it already forgot what task 1 was. So it's not going to be, for example, if task 1 is classifying images of animals, and then task 2 is vehicles, and then task 3 is some other classes, it will have a poor performance on classifying the very first task that it was learning. But why this happens? This happens because of something called the stability and plasticity dilemma. These networks, they have some set of parameters, some set of weights, and when we don't want to change them, that means that if we keep those weights fixed, we are going to preserve that knowledge, right? If we don't change those weights, then nothing is going to happen. We are still preserving that knowledge. But when we have a new task and we want to learn that, we need to tweak those weights. We need to change them. So we still need to have the ability to change those weights. That means we require plasticity in order to learn the new task. So the question here is, how do we make sure that we can change the weights to learn the new task without perturbing the existing knowledge in the network? There are a lot of methods for this. I won't go over all of them, but only over these 3 different ways of solving this issue, or at least diminishing it. One is called regularization. So what you do here is you impose restrictions on your weight updates. That means that if I have a network on task 1, I know that this is the space where my weights should land to solve that task. Then if I want to learn the second task, this is the other space where my weights should land for that second task. Instead of updating directly, instead of jumping from task 1 to task 2, which is going to make my network to forget what was task 1, I should try to jump into an overlapping area between those 2 tasks. So when you are updating your network, you need to find what are the weights that will learn the new task, but also will preserve the previous knowledge. And you can do that by doing this analysis. Another way is distillation, where you distill your knowledge, the knowledge from the previous model into the current model. So that means that when I am training a network, what I want to do is, if I have a new task that I need to learn, I will keep a copy of my classifier on the previous task. And then when I am learning the new task, I want my network to have the same response on the previous task. So in this way, what you're going to do is your network is going to try to learn the new task, but also the representations need to give the same output for the previous tasks. So imposing this, you tell the network you don't have to forget while learning the new task. And the last one is replay, which is one of the most successful family of methods. What they do here is, you have this incoming data, and then you're going to have a buffer where you're going to store some of that data. And then when you're learning a new set of data, you just mix that new set of data with this safe data that is in my buffer. So when you do this, you have, for example, some data from previous classes, right? I can have here some data from classifying animals, but then my new data is about vehicles. So when I pass those two combined to the network, I encourage the network to not forget what was before because it's still trying to classify that previous data. And usually this buffer is fixed. It's not an infinite buffer. You have like a limited capacity. From all those methods, one that I want to show you is remind, which is one that came from the laboratory where I am working on. This one is a replay-based method, so it uses this buffer for online continual streaming learning. So there are two different ways on how you could train your system when you have this incoming data. One way is called incremental batch learning, where, for example, you have task A, which is I want to learn to classify class cats. So in this case, you are allowed to loop over this data, this first set of data, as many times as you want until you learn this class, and then you go into the next one. And this could be learning a different class for dogs. And you again loop over it, and then you go to the next one. The problem with that is if you want to evaluate your network, you need to wait until it has finished looping over this task. And then right here in between, then you evaluate the network. So it's slow. On the online streaming learning setting, now you don't have that. You can still have that order between task 1 and task B, but now you have access only to one example at a time. So I take this image of this cat, I update my network, and then I go to the next image, and so on. And I cannot loop over this task because since I am looking at one image at a time, it's just gonna do one pass through the data. And this is more close. It's closer to how we experience data from, let's say, from videos or from the real world. So this method remind does that, and how it does it, it has a pre-training phase first. So, for example, I have my network. I take some data. If it's ImageNet, they usually take like 10 to 50% of the data with labels, and I do my supervised pre-training here. And then I switch into the online continual learning, where I will have one sample at a time, and I have that online update. But what I'm going to do is, remember I said we have this plasticity and stability dilemma. So what they do here is they split the network into two parts. One that is going to stay fixed. So this part is only going to contain the knowledge that we got from the pre-training. And another one that is going to be plastic. So this set of the network is going to be able to change in time. And they apply replay. That means that they have this buffer, right? But they do it in a more efficient way. Instead of just saving the images directly in this replay buffer, which we as humans, we don't save the images that we are looking at in a buffer in our brains. What we do is we actually save some sort of compressed representation. So they try to mimic that. They try to save compressed representation of these images in this buffer. And then whenever I have a new input, I will just decode these compressed representations and then mix it with the new sample that is coming and then train my network. So that's how they do replay. And with that, you could diminish forgetting. What they show is that all these previous methods like ICAR, Unified VAC, they work really good on the batch incremental setting, the one where you are able to loop over your data on every task. But then when you switch them to the streaming setting, which is more complicated, all of them break except for Remind, which performs pretty well on both of them. And then you can see on this plot here, what it's showing you is the top 5 accuracy over time. So that means, for example, I started on my pre-training point where I use, let's say, 100 classes to pre-train. And then I start learning all the next classes from the data set. So this is how many classes it's learning over time. And you can see that the performance decreases, but Remind is the one that decreases the less, having this orange curve. So that is showing you that Remind tends to diminish forgetting a bit less than or more than the other methods. However, this family of methods, they still assume that you have labels. Like all that I have been showing you is supervised continual learning. But before that, we talk about self-supervised, right? So, and these methods, they assume that you have these labels during the pre-training stage and also during the online continual learning. which it might not be true because during the online continual learning, we have this stream of data, so we might not have the labels available right away. And also we fall again into the problem that we need the labels to do this feature learning thing. So we have continual learning, but we are still using these labels to do feature learning. And also these methods, what they try to do is to not forget, right? So that means that they are trying to learn the current task, which it could be learning a current class, but also they try to not forget past classes that they already learned. But what about the new classes that are coming? That means that these methods might overfit to the current and the past class, and they are learning features that might not be helpful for the future classes. So that's why we could have a decrease in performance when we are learning more and more classes. So the question here is, can continual learning be more efficient on feature learning? That means, can we learn features that not only take into account the current task and the previous classes, but also the future classes that we haven't seen yet? And that's where it comes the combination between self-supervised and continual learning. So first, I'm going to show you one of my works that was published in BMPC in 2021 called Self-supervised Training Enhances Online Continual Learning. As I said before, in online continual learning, we have these two stages. You do your pre-training, which is usually supervised, so we have the supervised pre-training, and then you do your online continual training. And when you're doing this on an ImageNet data set, for example, they use 10 to 50% of the classes, which is a lot. The issue is that this supervised pre-training is prone to learn features that might not generalize on the second stage of learning. And this gets even worse if during pre-training I have a small set of data. For example, I could have only 10 classes. And let's say those 10 classes are only about plants. But then later on in continual learning, I need to learn about vehicles. So those features that I learned about plants might not be useful for later on because the amount of data here was small. That's why they use 10 to 50% of data, because they try to include as many classes as they can, so supervised learning will learn features that are good enough. But the idea here is, let's replace that supervised pre-training and let's just use self-supervised pre-training, because we know that they generalize better than supervised learning, right? And we hypothesize that this method is a better fit for pre-training of online continual learning, because SSL features might transfer better than supervised ones later on. So we test this using pre-training. We have the supervised one, which is our baseline, but then we tried 3 different self-supervised learning methods, and then we tried 3 different online learning methods. Deepest LDA, which is another method that was developed by the laboratory where I'm working on, they don't use replay. What they do is every time they see a new class, they learn a mean vector of that class, and then they learn a shared covariance matrix across all the classes. So that means that you're going to have like a Gaussian space for each class. And then when you have a new sample coming in, you just try to find which class is the closest to that sample in that space, and that's how you classify it. Then we have online softmax, which is just it's a normal way to train a network with a softmax classifier. We can fix the network, and then we do replay on the representations right before softmax. And remind, which is the one that I explained before. We test this on ImageNet, and we train different pre-training sizes. So instead of using 10 to 50% of the data, we are using 1% to 10%. So we know that this is the extreme case where supervised breaks. After doing experiments, we found that self-supervised pre-training outperforms supervised pre-training, especially when we have a small set of classes. So on these images, what they're showing you is the increase over the supervised pre-training. And this is after we have done the pre-training stage, and then we do the online learning stage, and then we have some accuracy performance. So what they're doing is how much better that performance is compared to the supervised one. And you can see that for all those different methods, it depends. Some of the self-supervised methods, they actually decrease performance, but as you start to decrease the number of classes that you use in your training set, you get way more better advantage by using a self-supervised method compared to a supervised method during pre-training. So with this, we set a new state of the art on online continual learning by pairing remind with swap, which is this blue curve now. So this is the same plot that I showed you before, but now we have this extra blue curve, which is that pair of remind plus swap. And you can see that now the curve decreases even less. But something better now is that we don't need labels for pre-training because we are using swap, which is a self-supervised method. Sorry, but another thing is that you see that almost all these methods, or at least remind and remind with swap, they start at the same point, right? This is right after pre-training. They have the same performance almost. But then later on, remind plus swap it doesn't decrease as much as remind. So we think that this is happening because the features that we learn after pre-training, they generalize better later on when you use self-supervised pre-training as well. But there is still a gap, right? This dotted line is showing you the offline setting. That means you're not doing any incremental online learning. You just take all data set, you shuffle it, and then you train your network. So we still cannot reach that performance, which is our upper bound. And we think that that is happening because even though we have this nice effect on self-supervised pre-training, that effect might diminish while you are training in more and more classes during time. So it's not enough just to do it on the pre-training stage. So can we use self-supervised learning a better word than just in pre-training? So for that, I want to show you this work called Reduce the Difficulty of Incremental Learning with Self-Supervised Learning. What they do here is they use the self-supervised learning laws as a regularization signal during the continual learning stage. So, and they do this so they can ensure that you will have feature diversity. So on this equation, this loss Ln is showing you just the normal cross entropy loss that you do to do your supervision. So you have labels and you check how your predictions are compared to the labels. Then you have this other loss called loss incremental, which comes from the continual learning part. So this loss is ensuring that you won't have forgetting. But besides those two, now they add this extra loss that is called SSL, which in this case is just a rotation prediction task. So with this, what they are telling to the network is, okay, I want you to learn the classes because this one will have the labels. I want you to not forget because this one is penalizing if you're changing the weights too much or if you're just having forgetting. But also, I want you to learn features that don't necessarily relate to the class that you're learning or to the forgetting, which is the previous class. I want you just to learn some features that are a bit more general. And they do that with this rotation prediction. And on the table on the right, they show that if you pair that with different methods that do continual learning, like LWF or EWC, or even replay-based methods like experience replay, you always get gains in performance by just plugging in this rotation prediction task. Another way to do this, they show it in this paper called task agnostic representation consolidation, which is a self-supervised based continual learning approach. What they do here is, if we have the incremental batch learning stage, I said that in this case, we are able to loop over this first task called task A. So we can do as many loops as we want there until we learn that data. While we are doing that, what they do is they split the learning into two different parts. They have something called task agnostic learning and something called task specific learning. So on task agnostic learning, what they do is, I'm gonna learn features, but just by using a self-supervised learning loss. So that means that at the very beginning of training, while learning that task, I'm not gonna worry about learning the class. I'm just gonna worry about learning good features from that set of data. So they do that, but also you need to deal with forgetting. So they have this memory buffer, which is the replay-based way of not having forgetting. So after that, when they are done with that section, then they change to the task-specific learning, where now you don't use the self-supervised learning loss. Now what you use is your classification loss, which is the one that's gonna tell the network to learn the class. And then you have this extra rotation prediction task, which is the same one as I showed before. So this one will tell the network to not focus too much on learning features for that class, also solve this task, which could give you some general features. Just by doing that, they show their method is called TARC. If you pair that with some experience replay methods, you can get a really big boost in performance compared to not doing that. So if you use the normal experience replay method. And they try that on different data sets. And also different, not only in class incremental learning, which is what I have been talking about, in other tasks like domain incremental learning. But there is an issue here, right? On these methods, I am always saying they have these classification logs, the one that uses the labels. But we said that the real world might not have labels, right? So the previous methods were only using self-supervised learning, but not in their fully potential way. So we want to deal with this too. We need to do continual self-supervised learning. There is a recent paper from this guy, Abhinav Gupta, which is really famous in the field, called The Challenges of Continuous Self-Supervised Learning. They define what continual self-supervised learning is. So on a normal setting, we have the conventional self-supervised setting where we have our finite data. Now this data is independent and identically distributed. That means that each image is independent from each other and the classes are identically distributed. So I find the same number of images for each class. And also the semantics is stationary. That means that if I have 1,000 categories in this data, that's it, right? I'm not gonna have more categories. So I will be able to learn a stationary semantics. But continuous self-supervised learning should deal with a stream of data, which is, they call it infinite data, but it's just saying we have data coming in all the time. And also that data, for example, if it's something from self-supervised learning, from self-driving cars, the images are not independent. They have a temporal correlation, right? And they might not be stationary semantics because we are seeing new things in time. Like, for example, they are seeing a lot of cars here, but then if it goes into a more nature area, it's going to start to see plants and other things. So we don't have a stationary semantics. So to solve this, they propose to use replay in a different way. So in this case, we don't have labels. We don't have anything. We just have a stream of data that is coming and we somehow need to learn something from it. So what they say here is instead of waiting for your data to come from the stream, accumulate it, and then learn using this self-supervised method, and then do that again, which is not efficient, they propose to have a replay buffer, which is gonna decorrelate how the network and the streaming are gonna be connected. So in this replay buffer, you're gonna have your data coming in. You will fill out that buffer, but you will have the option to learn in any time step using your method. So now your network is only gonna look at the buffer. It's not gonna look at the streaming of data that is coming in. It's only gonna look at the buffer, and you just try to manage that buffer from the incoming data. And they call it this buffered self-supervised learning. So, and they show that if you do that, just adding that buffer, you can have better performance compared to not doing that, which is the conventional way. But there is an issue. If we want to deal with images that come from video data, we are going to have a lot of those images that might be similar to each other, right? So they might not give me any meaningful information if I have two frames that are almost the same. So what they do here to deal with this non-independent data, they use something called minimum redundancy on the replay buffer. So what they do here is when you are filling up the buffer, you're going to look at the cosine distance between two images. And then you're going to select the pair that has the lowest, well, the two pairs that are the closest ones, and then you're going to delete one of them. So by doing that, you're deleting one image that is really similar to another one. So then when you do that several times, you will end up with a buffer that has more diversity of images in it. And they show that if you do that in a data set like kinetics, which is a video data set, you get a gain in performance like a lot from just doing buffer SSL or the conventional SSL. So this is how you could deal with this non-independent data. But then also we had the issue about semantics, right? So in this case, let's say, for example, our network is seeing a lot of just vehicle stuff, and then after a while it changes from that to see a lot of animal stuff. So if we have the normal replay buffer, we will be accumulating images from only that semantics. And then when we switch to another one, we might have only that semantics inside of my buffer. So what they say is that just using the same trick that they said before, the minimum redundancy, you could have a semantic rich buffer. Even though it's just calculating the cosine distance within the images, it happens that images that have the same semantics, they will likely be close to each other in the representation space. So when you apply this deleting, you will have a richer semantics in your buffer. And they show that works better on this split ImageNet 21K data. But what they did is, if I have this data set, I could split them into different subsets that are going to have the same semantic, different semantics. So for example, this data P1, they could be only animals, and then this data P2 could be only vehicles. So when you train your network and going over each of them, you will see that if you use this mean red way of treating the buffer, you get less decreasing in performance over time. And then a final work that I want to show you on continual self-supervision is this one called self-supervised models are continual learners. What they do here is, it's a bit different. They went a bit more after what do we do to the network instead of just dealing with the replay buffer, right? On the previous work, it was all about just the replay buffer. But here, they try to do something that is related to distillation. So what you do here is, if I have my set of sequential data, I have the first data set DT and then other data sets that are coming in time. I'm going to do my augmentations, as I said before, in self-supervised learning. When you do two different perturbations to the image, I pass those through the network, and then I do my self-supervised loss, which is, it could be like the contrastive loss that I showed way before. That's the normal way to train your network. But what they do to deal with the problem of forgetting is that you will keep a copy of your network from the previous step. This T-1 is telling you it's a copy from the previous step when I was learning these different data sets. So what they do here now is you will have that output, and then you are supposed to be able to predict that output of your previous network just using an extra predictor step here. And how they do that, they just plug in these two into the same self-supervised learning loss. So what they do here in this equation is I will have my self-supervised loss that is using the two augmented images, but then I will have another one where it's using the predicted one for ZA and the C bar A, which is the one coming from the previous step. So I am trying to push together the one from the augmentations, but also I am trying to push together the ones from the current and the previous one. So by doing that, they ensure that forgetting is going to diminish while learning these features. On this table, they show you the results. Their model is called Castle. And what they did is they took a bunch of self-supervised learning methods that are here, Sinclair, that I explained, and other ones like Barlow twins or Vijol. And they tried to apply the common continual learning methods that are out there off the shelf on these self-supervised learning methods. But what they show is that if you do this way of preserving knowledge, you can get better performance. Yeah, so now I will go to quick summary. So on this presentation, I have shown you that self-supervised learning now rivals supervised learning, but this is on the linear evaluation task, right? But on self-supervised learning, if you do your linear evaluation on a different data set, that's where self-supervised learning shines. because now it generalizes better than supervised learning on those different downstream tasks. Supervised continual learning is the one that deals with this stream of data and the incremental updates, but you need the labels if you're doing this way of training continually. And you could use self-supervised learning in supervised continual learning, as I show in my work, where we try to do that on the pre-training stage, but also if you can just plug in as a regularization signal while doing the online continual learning. And that results in better performance because we are pushing the features to be a bit more general than just learning the current task and preserving the knowledge of previous tasks. And when you don't have labels available, not even during the continual learning phase, continual self-supervised learning is recently being studied. And some final thoughts. Current self-supervised learning, it's not data efficient. So in this plot, what I'm showing you from the swap method, they show the number of epochs, that means how many loops you do through your data, compared to the accuracy that you can get when you train these methods. And you can see that the supervised value is around 76. So if you train for 100, you're far away still. But then you need to train at least 800 epochs, which is a lot because they're saying that takes 50 hours of training. And you're using 64 GPUs, that's a lot. To reach a performance that is not even there with the supervised learning. And the supervised learning only needs 100 or maybe less than 100. So they are not data efficient. They need lots of epochs, also big batches, because they need to have a big batch of data to pass it through the network. So we need data efficient SSL methods if we want to combine this with continual learning in a better way than the ones that I showed. But if we are using the ones that we have right now, we know that SSL can help continual learning on features transfer. That means that we are gonna, while learning, we are gonna be able to learn new classes efficiently and faster because we are trying to learn features that are more general. But for this, we actually need a better understanding of feature learning, of continual learning. There are not many works that are saying how these features are changing in time while doing continual learning. That needs to be explored if we want to combine these two better. And one final thought is that continual self-supervised learning can be used to incrementally update feature structures. I mean, if you don't have labels, but you have data incoming, and you want to learn some features from it, you could just do like the last two methods that I show you to incrementally update your feature structure. And that's everything that I have to say. Thank you.